In the quiet expanse beyond familiar environments, the universe maintains conditions that are often misunderstood, and tonight this exploration moves gently into those conditions to observe how energy and temperature behave far from planetary surfaces. As this narration unfolds slowly and without urgency, it may accompany you through different moments of the day or night. And if you feel comfortable, you may share in the comments where you are listening from and what time it is, because understanding how these stories travel through the world adds quiet context to this journey. If this style of calm scientific exploration supports your rest focus or long listening, you may choose to subscribe and leave a simple like as a way of continuing this steady flow of content. Now the narrative continues without interruption into the underlying physical reality that shapes space itself. In the broad environment beyond planetary atmospheres, temperature is defined through the motion of particles rather than through sensation, and this distinction becomes essential when considering regions where matter is sparse and interactions occur over vast distances. Temperature in physical terms represents the average kinetic energy of particles within a system, and when particles are few and far apart, this average describes individual motion rather than collective warmth. Space contains atoms, ions, electrons, and photons that move under the influence of fundamental forces, and their energies vary widely depending on location and exposure to radiation. In interstellar regions, particles drift for long durations without frequent collisions, and because collisions are rare, energy exchange proceeds slowly, and no unified thermal state emerges in the way it does within dense matter. The environment therefore maintains extremely low bulk temperature, even while hosting particles that individually carry substantial energy. This separation between particle energy and environmental temperature explains how space can be described as cold while simultaneously containing energetic radiation and fast-moving particles. One of the most stable references for understanding cosmic temperature is the pervasive background radiation that fills the universe uniformly. And this radiation field represents a remnant from early cosmic conditions and establishes a baseline thermal presence that permeates even the most empty regions. Matter isolated from other influences will gradually approach equilibrium with this background through radiation exchange over immense timescales. And this slow process defines the minimum temperature toward which isolated systems tend to move. Near stars, the situation changes because radiation intensity increases dramatically and particles absorb energy from photons, raising their kinetic motion and producing regions of high temperature localized around energy sources. These regions exist alongside cold voids, creating sharp contrasts across distance while remaining stable within their own scales. Temperature in space, therefore, cannot be expressed as a single universal value, but must be understood as a layered structure shaped by radiation density, particle motion, and field interaction. Plasma plays a central role in this structure because charged particles respond collectively to electromagnetic forces, forming distributions that carry energy across space without requiring dense matter. Within plasma environments, waves propagate along magnetic field lines, transporting energy in organized patterns and contributing to localized heating and cooling without abrupt transitions. Measurements of these conditions rely on indirect observation through spectroscopy, radiation intensity analysis, and particle detection. And these methods reveal smooth gradients and steady distribution rather than chaotic fluctuation. This calm distribution of thermal energy influences how matter behaves on large scales because cooling allows gas clouds to contract under gravity, while heating counterbalances collapse and regulates structure formation. Galaxies emerge through this balance, and stars form only where temperature and density permit sustained contraction. Planetary systems depend on surrounding thermal conditions because radiation governs atmospheric stability, surface equilibrium, and long-term energy balance. Spacecraft operating in space must manage heat through radiation alone because convection is absent, and this requirement reflects the fundamental nature of thermal exchange in vacuum. Understanding the real temperature of space therefore matters not because of sensation, but because it governs motion stability and change across all cosmic systems. Temperature acts as a quiet regulator shaping evolution without urgency and without dramatic shift. Across long durations, energy flows steadily and predictably, maintaining balance through gradual exchange. This perspective reveals space not as an extreme environment of contradiction, but as a coherent system where cold and energy coexist through well-defined principles. The true thermal nature of space emerges through patient observation and careful interpretation, and it supports a calm understanding of the universe as a place governed by continuity, balance, and slow transformation, rather than sudden extremes. And within this steady framework, temperature remains one of the most subtle yet influential properties, guiding the behavior of matter from the smallest particles to the largest structures across the cosmos. In environments where air and dense matter are absent, temperature must be understood through radiation balance rather than through surrounding warmth, and this distinction shapes how objects and particles behave in open space. When a material body moves through vacuum, it does not exchange heat through contact with an atmosphere, but instead gains and loses energy only through absorption and emission of electromagnetic radiation. This process unfolds gradually and depends strongly on orientation, surface composition, and distance from radiation sources. A surface facing a star may absorb photons and increase in internal energy, while another surface in shadow simultaneously releases energy into space and cools. These opposing processes can occur on the same object at the same time because no ambient medium exists to equalize temperatures between regions. This leads to persistent thermal gradients that remain stable until radiation conditions change. Spacecraft illustrate this principle clearly because their temperature is governed not by the surrounding emptiness, but by how efficiently they absorb, reflect, and emit radiation. Engineering designs therefore rely on controlled emissivity, insulation, and rotation to maintain equilibrium rather than on insulation against cold air. The broader space environment follows the same logic because regions exposed to stellar radiation maintain higher particle energy, while distant regions gradually approach equilibrium with background radiation. Photons travel freely across space, carrying energy independent of local temperature, and when they encounter matter, they may transfer that energy, altering the kinetic motion of particles within the receiving system. This explains how sunlight can warm an object even though the surrounding space remains cold, and why temperature measurements always refer to specific systems rather than empty volume. Gas clouds dispersed through space demonstrate how radiation balance governs thermal state because their temperature reflects the competition between energy gained from nearby stars and energy lost through emission and expansion. When energy input is low, these clouds cool slowly, allowing gravity to act more effectively, and over long durations, denser regions may form without sudden change. When energy input is higher, thermal motion counteracts collapse and maintains diffuse structures. This slow interplay establishes the pace of cosmic evolution because heating and cooling regulate how matter organizes itself across time. Even highly energetic particles such as cosmic rays move through cold environments because their energy is concentrated in individual motion rather than shared among many particles. Such particles pass through vast regions without significantly raising ambient temperature, reinforcing the idea that temperature describes collective behavior rather than isolated events. Observations confirm that the coldness of space is not a lack of energy, but a reflection of how energy is distributed thinly across immense volumes. Over extended timescales, radiation gradually transfers energy between systems, guiding them toward equilibrium with the surrounding radiation field. This quiet exchange proceeds without interruption, shaping structures gently and predictably. Understanding this mechanism is essential for interpreting astronomical data, because apparent contradictions resolve when temperature is viewed as a statistical property rather than a sensory one. Within this framework, the universe appears coherent and stable, governed by gradual adjustments rather than abrupt shifts. Thermal behavior becomes a regulating influence that sets limits and conditions rather than a force that imposes dramatic change. This steady regulation allows matter to persist, evolve, and organize in a calm and continuous manner, across scales ranging from microscopic particles to planetary systems and beyond. As distance from stars increases, thermal conditions become dominated by slow radiative exchange rather than immediate energy input, and this shift defines the character of deep space environments. Particles drift through vast volumes where encounters are rare, and because collisions occur infrequently, there is little opportunity for rapid redistribution of energy. Each atom, ion, or molecule carries its own kinetic history shaped by prior interactions. Yet the surrounding environment reflects only the statistical average of countless isolated motions. In these regions, the background radiation field becomes the primary reference for temperature because it permeates all space uniformly and establishes a steady baseline. Matter that is isolated from local sources of radiation will gradually emit energy through electromagnetic processes until its emission balances the faint absorption from this background. And this balance is reached slowly without oscillation or instability. Dust grains provide a clear example because they cool by radiating infrared energy while absorbing minimal ambient photons. Over long durations, they settle into stable thermal states determined by size, composition, and exposure. Interstellar gas behaves in a similar manner because its temperature reflects the competition between weak heating and continuous radiative cooling. Where heating is negligible, temperatures remain close to the lowest values permitted by the surrounding radiation field, creating regions that appear uniformly cold when averaged across large scales. This uniformity does not imply inactivity, because chemical reactions, particle interactions, and field dynamics continue at reduced rates. Temperature in this context acts as a regulator that limits reaction speed and structural change, rather than eliminating activity entirely. When disturbances such as shock waves or radiation fronts pass through these regions, they introduce localized heating. But once the influence fades, the environment returns gradually to equilibrium, without abrupt transition. Observational data show that even after energetic events, the surrounding medium cools steadily through radiation and expansion until balance is restored. This slow recovery highlights the stabilizing role of thermal processes in preventing runaway behavior. On galactic scales, this regulation shapes how matter cycles between diffuse and condensed phases, because cooling allows gravity to act while heating resists collapse. The interplay unfolds gently across immense timescales without urgency. The background radiation ensures that no region cools indefinitely below a defined limit, setting constraints on molecular formation, phase behavior, and long-term stability. Temperature, therefore, becomes a quiet boundary condition, guiding what is possible rather than an active force imposing change. Through this lens, deep space appears calm, consistent, and patient, governed by gradual energy redistribution rather than dramatic fluctuation. This steady thermal character allows matter to persist, evolve, and reorganize slowly across cosmic time without disruption. As attention moves toward regions influenced by planetary bodies, temperature becomes shaped not only by radiation balance, but also by gravitational confinement and particle interaction. And this introduces additional layers to thermal behavior in space. Planets, moons, and atmospheres gather matter into denser arrangements, and where density increases, collisions become more frequent, allowing energy to redistribute more efficiently within the system. This transition marks the boundary where temperature begins to resemble familiar definitions, because collective motion emerges from many interacting particles. Atmospheres retain heat through repeated collisions and absorption of radiation, creating stable thermal layers that respond gradually to changes in energy input. Above these atmospheres, space resumes its sparse character, and the contrast between confined warmth and surrounding cold becomes pronounced. This contrast matters because it governs atmospheric escape, surface conditions, and long-term planetary evolution. Particles at the upper edges of atmospheres may gain enough energy from radiation to escape gravitational binding, and this slow loss reshapes planetary environments over geological timescales. Temperature, therefore, becomes a determining factor in whether a planet can retain gases, liquids, or complex chemistry. In the absence of sufficient thermal regulation, atmospheres' thin surfaces cool, and chemical activity diminishes gradually rather than abruptly. Magnetic fields add another layer by guiding charged particles and influencing how energy is deposited into upper atmospheric regions. These interactions create auroral heating zones, where energy flows along field lines and disperses into surrounding particles. Even here, the process remains regulated and steady, because energy input is distributed across large areas and moderated by radiation emission. Spacecraft measurements reveal that these regions exhibit elevated temperatures locally, while the surrounding space remains near background equilibrium. This coexistence of warm, confined zones and cold, open regions illustrates how temperature in space depends strongly on structure and containment. Without confinement, energy disperses and temperatures remain low, while with confinement, energy can accumulate and sustain higher thermal states. This principle applies across scales, from planetary atmospheres to stellar interiors, where gravity holds matter together, allowing intense heating through compression and fusion. Outside these structures, energy radiates outward and temperature decreases smoothly with distance. The gradient between hot cores and cold surroundings is continuous and predictable, reflecting conservation laws rather than instability. Understanding these gradients is essential because they explain why habitable conditions exist only within narrow ranges where energy input and loss remain balanced. Planets located too close to energy sources experience excessive heating, while those too distant cool beyond thresholds that support complex processes. Space between these extremes remains calm and cold, acting as a buffer that moderates change over time. Temperature, therefore, serves as a quiet filter determining which environments can host long-term stability and which evolve toward simplicity. Observational data confirm that these transitions occur slowly and consistently, allowing systems to adapt or fade without sudden disruption. Over long durations, the distribution of temperature shapes orbital dynamics, atmospheric chemistry, and surface evolution through gradual influence rather than forceful intervention. This slow shaping aligns with the overall character of space, where change unfolds through accumulation and balance rather than immediacy. Within this context, the role of temperature extends beyond measurement and becomes a guiding parameter that quietly defines the boundaries of structure persistence and transformation across planetary systems and the surrounding void. As consideration extends outward towards stellar environments, temperature becomes intertwined with radiation pressure fusion processes and long-term energy transport, and these regions demonstrate how extreme thermal states coexist with surrounding cold through orderly gradients rather than abrupt boundaries. Within stars, gravity confines enormous amounts of matter, allowing density and pressure to rise until nuclear reactions release energy continuously. This energy moves outward through radiation and convection and gradually escapes into surrounding space where it disperses without resistance. The stellar surface marks a transition where confined heat gives way to open radiation, and beyond this boundary, photons travel freely, carrying energy across vast distances without raising ambient temperature uniformly. Nearby particles absorb a fraction of this energy and increase their motion, while the majority continues onward, maintaining the cold character of interstellar space. This outward flow establishes predictable temperature gradients that decrease smoothly with distance, and these gradients remain stable over long durations because energy output and loss remain balanced. Stellar winds composed of charged particles extend this influence further, carrying thermal energy and momentum into surrounding regions and interacting with magnetic fields to form extended structures. Yet even these interactions unfold gradually and distribute energy thinly across space. Temperature measurements in such regions reveal elevated particle energies locally, while the broader environment remains governed by background equilibrium. The contrast highlights again that temperature reflects collective behavior rather than isolated intensity. Clusters of stars amplify these effects because overlapping radiation fields raise regional temperatures modestly while still preserving large-scale coldness due to rapid energy dispersion. Gas within these clusters responds by adjusting pressure and density, and this response shapes future star formation by regulating collapse rates. When energy input exceeds cooling capacity, matter remains diffuse and stable, while when cooling dominates, gravity gains influence and structures condense slowly. This balance operates continuously without sudden shift and illustrates how temperature governs evolution through moderation rather than force. Supernova remnants briefly disrupt this equilibrium by injecting large amounts of energy into surrounding space. But even these events resolve into gradual cooling phases, where radiation emission and expansion restore balance over extended timescales. Observations show that shock-heated gas cools predictably, forming shells and filaments that fade without oscillation. The surrounding space absorbs this energy thinly, preventing widespread heating and preserving overall stability. Temperature thus functions as a damping parameter, ensuring that even dramatic events integrate smoothly into the larger system. Across galactic environments, this damping maintains coherence and prevents runaway heating that would otherwise erase structure. The steady decline of temperature with distance from energy sources defines habitable zones, chemical activity ranges, and long-term material cycling. Without these gradients, the universe would lack the ordered diversity observed across scales. Understanding stellar thermal influence therefore matters, because it explains how energy is distributed without disturbing the calm character of space as a whole. Heat is generated intensely, yet released gently, allowing cold and warmth to coexist in balanced proportion. This coexistence supports the formation, persistence, and transformation of matter through gradual pathways rather than abrupt change. Within this framework, temperature emerges as a continuous field guiding motion, interaction, and possibility across stellar systems. and beyond while maintaining the overall stillness that characterizes the vast regions between luminous sources. As the view expands to the largest scales, temperature becomes a property of populations and histories rather than locations. And this shift clarifies how the universe maintains coherence over immense distances and durations. On cosmological scales, matter and radiation evolve together under expansion, and this expansion stretches wavelengths, reduces energy density, and guides the gradual cooling of space as a whole. The pervasive background radiation provides a uniform reference that reflects this long history and establishes a calm thermal presence everywhere. Particles moving through this expanding environment experience decreasing interaction rates and diminishing opportunities for energy exchange, which reinforces the persistence of low average temperatures. Galaxies drift apart, and the radiation between them thins further, yet the statistical description of temperature remains meaningful, because it captures the average state of countless independent motions. Within this context, temperature is not a sensation, but a summary of distribution describing how energy is shared across vast ensembles. The importance of this summary becomes evident when considering structure formation, because cooling thresholds determine when matter can transition from diffuse states to bound configurations. As the universe expands, cooling favors condensation at appropriate times, allowing galaxy stars and planets to form gradually rather than simultaneously. Once formed, these structures generate local heating through radiation and dynamics, while the surrounding space continues its slow cooling trend, maintaining contrast without instability. Measurements of distant radiation show remarkable uniformity, which indicates that thermal conditions on the largest scales are smooth and continuous rather than patchy. This smoothness supports the idea that expansion and radiation exchange act as global regulators, smoothing extremes over time. Temperature therefore matters, because it encodes the balance between expansion, energy generation, and radiation loss, and this balance determines the pace of cosmic evolution. When energy densities were higher, interactions were more frequent, and temperatures were elevated, enabling rapid change, while, as expansion progressed, interactions slowed, and temperatures declined, ushering in eras of stability. The present environment reflects this matured state where change continues, but at a measured pace. This measured pace allows long-lived structures to persist and complex processes to unfold without disruption. Even the coldest regions retain thermal meaning, because background radiation sets a floor that prevents indefinite cooling. This floor influences chemical reaction rates, phase stability, and the longevity of matter in intergalactic space. Observations confirm that over billions of years, the average temperature of space has decreased predictably following expansion dynamics rather than random fluctuation. This predictability reinforces confidence in the underlying physical principles and supports a calm understanding of cosmic order. Temperature becomes a quiet record keeper, tracing the history of energy flow from early high-density conditions to the present sparse state. Reading this record allows scientists to reconstruct timelines and understand why the universe appears structured yet tranquil. Within this framework, the real temperature of space matters not because it feels cold, but because it defines what processes can occur and when they can occur. It limits reaction speeds, governs stability, and moderates transformation through steady influence. This steady influence ensures continuity across scales, from the smallest particles to the largest voids. As expansion continues, temperatures will decline further and interactions will slow even more, yet the same principles will apply, guiding matter gently toward new equilibria. The universe thus remains governed by calm thermal logic, where energy disperses gradually and balance prevails. Through this lens, space is understood as an environment shaped by patience, where temperature serves as a silent organizer, maintaining order across time without urgency or disturbance. As understanding deepens, temperature can be seen as a unifying thread that links microscopic motion to cosmic scale order, and this perspective reveals why careful definition matters when interpreting space as an environment. Temperature does not reside in emptiness itself, but emerges from how matter and radiation interact within given boundaries and histories. When particles are isolated, their individual energies persist without collective exchange, and only statistical treatment yields a meaningful description. This statistical nature allows temperature to remain a useful concept, even where direct sensation is impossible, and it enables comparison across regions that differ dramatically in density and energy input. In space, radiation serves as the primary mediator of thermal interaction, and through emission, absorption, and scattering, energy flows steadily between systems without reliance on contact. This radiative exchange establishes equilibrium states that are approached asymptotically over long durations rather than reached abruptly. And this gradualism defines the calm character of thermal evolution beyond planets. Objects exposed to radiation adjust their internal energy until outgoing and incoming flows balance, and this balance may shift slowly as conditions change. Materials respond according to their emissive properties and structural composition, and these responses shape long-term stability. Ice, dust, rock, and gas each interact with radiation differently, and therefore occupy distinct thermal niches even within the same region of space. This diversity allows a range of physical states to coexist without conflict because energy distribution remains thin and controlled. The absence of dense media prevents rapid transfer and ensures that changes propagate gently rather than explosively. This gentle propagation underlies the persistence of order across vast distances and explains why large-scale structures remain coherent over cosmic time. Temperature thus functions as a moderator that tempers energy flow and prevents extremes from spreading unchecked. Even where intense energy is released, radiation disperses it broadly and thinly, maintaining overall balance. This moderation influences chemical pathways because reaction rates depend on available energy, and stable temperature ranges permit complex molecules to form and survive. In cold regions, reactions proceed slowly but steadily, allowing accumulation over time rather than rapid transformation. These conditions favor longevity and gradual complexity, which align with the broader pattern of cosmic evolution. When viewed through this lens, the significance of space temperature becomes clear because it sets the tempo of all physical processes beyond planets. A slow tempo fosters stability, predictability, and continuity, and these qualities allow systems to endure and evolve without disruption. Scientific observation confirms that temperature gradients remain smooth and that deviations resolve into equilibrium without oscillation. This behavior reflects underlying conservation principles that govern energy distribution universally. By respecting these principles, models accurately describe phenomena across scales and reveal a universe that operates with consistency rather than volatility. Temperature measurements therefore serve as anchors connecting theory to observation and ensuring coherence in interpretation. They inform understanding of star formation, planetary climate, interstellar chemistry, and cosmic expansion alike. Without this framework, descriptions would fragment and lose context. Within the quiet expanse of space, temperature stands as a subtle yet pervasive influence, shaping motion, structure, and possibility through patient regulation. It matters because it quietly determines what can persist, what can change, and how change unfolds over time. Through steady radiative exchange and statistical balance, temperature guides the universe towards states of enduring order without urgency. This enduring order reflects a cosmos that evolves through calm adjustment rather than forceful intervention, and invites extended contemplation without disturbance. As the focus turns toward measurement and interpretation, the meaning of temperature in space becomes inseparable from the tools and methods used to observe it, and this introduces another layer of calm complexity. Because direct contact measurement is impossible in most regions, scientists rely on radiation spectra, particle counts, and energy distributions to infer thermal states. These methods translate physical interaction into data that reflects average behavior rather than individual extremes. Spectroscopy reveals how atoms and molecules emit and absorb energy at specific wavelengths, and the intensity and shape of these signals indicate the kinetic motion of particles within a region. By analyzing these patterns, researchers determine temperature without disturbing the environment, and this non-invasive approach aligns with the delicate nature of sparse systems. Particle detectors aboard spacecraft measure velocity distributions of ions and electrons, and from these distributions, temperature is derived as a statistical property describing spread rather than magnitude. This approach reinforces the idea that temperature summarizes collective motion rather than isolated speed. In regions where plasma dominates, magnetic and electric fields influence particle trajectories, and this influence must be accounted for when interpreting thermal data. Careful separation of field-driven motion from random kinetic behavior ensures accurate representation. Radiation-based measurements extend across vast distances, allowing remote sensing of thermal conditions in environments far beyond direct reach. Infrared observations capture the cooling of dust clouds, while microwave measurements trace the uniform background that permeates space. These complementary methods provide a coherent picture where local variation exists within global stability. Interpretation requires patience because signals are often faint and changes occur slowly, and long observation periods are necessary to reveal meaningful trends. This patience mirrors the gradual nature of thermal evolution itself and prevents misinterpretation driven by short-term fluctuation. Calibration against known references maintains consistency across instruments and missions, ensuring that temperature estimates remain comparable over time. This consistency matters because long-term records reveal how environments evolve rather than how they fluctuate momentarily. Through accumulation of data, patterns emerge showing steady cooling expansion, driven shifts, and localized heating events that resolve predictably. Understanding these patterns allows models to describe future behavior without urgency or alarm. Temperature measurements thus serve not only as descriptors, but as guides that inform expectations of stability and change. They help identify regions where matter may condense, remain diffuse, or transition between states. In planetary exploration, accurate thermal interpretation protects equipment and informs mission design, because survival depends on managing radiative balance rather than resisting cold air. Insulation, reflective surfaces, and controlled emission become primary strategies aligned with the physics of vacuum. This practical application demonstrates how abstract thermal concepts translate into real outcomes without drama. On a broader scale, measurement of space temperature validates fundamental theories of radiation expansion and energy conservation, and confirms that these principles operate uniformly. Deviations are rare, and when observed, they prompt refinement rather than rejection because underlying stability persists. Temperature, therefore, becomes a bridge between theory, observation, and application, linking quiet physical law to tangible understanding. It matters because it allows comprehension without disturbance and prediction without urgency. Through careful measurement and interpretation, the calm thermal structure of space is revealed as ordered, intelligible, and continuous. This revelation supports a steady view of the universe, where knowledge deepens through observation and balance rather than confrontation. Within this measured approach, temperature remains a reliable indicator guiding exploration, interpretation, and long-term understanding across the vast and tranquil expanse of space. As reflection continues, temperature reveals its role as a constraint that quietly defines limits within which all other processes unfold. And this role becomes especially clear when considering longevity and decay across cosmic environments. Energy once introduced into a system does not vanish, but redistributes gradually through radiation and interaction, and temperature tracks this redistribution over time. By following temperature changes, scientists infer the history of energy flow and anticipate future states without invoking sudden transitions. Cooling curves describe how objects release energy steadily, and these curves depend on composition, structure, and exposure rather than on surrounding emptiness. A cooling star remnant releases heat predictably through radiation, and its temperature decline marks the passage of time more reliably than visible change. Similarly, planetary bodies cool internally over geological durations, and their surface conditions reflect a balance between internal heat radiation input and emission to space. This balance evolves slowly, allowing stable climates or gradual shifts rather than abrupt collapse. In interstellar clouds, temperature decline permits molecules to form and persist, and these molecules record chemical pathways that unfold over long periods. Their presence signals conditions that have remained calm and consistent long enough for complexity to arise. Temperature, therefore, acts as a gatekeeper, determining which reactions proceed and which remain suppressed. High temperatures favor rapid reactions and simple products, while low temperatures favor slow accumulation and delicate structures. This selective influence shapes the chemical landscape of space and contributes to diversity without chaos. The absence of rapid thermal exchange ensures that once conditions are established, they persist long enough to have lasting effects. This persistence is essential for structure formation because gravity requires time to amplify small differences, and temperature regulation provides that time. When environments cool gradually, density contrasts can grow and organize matter into coherent forms. When heating dominates, matter disperses and returns to diffuse states without violent disruption. This reversible behavior underscores the moderating influence of temperature as a stabilizing parameter. Across cosmic scales, the same principle applies from microscopic grains to massive halos. Temperature gradients guide motion, but do not force it, and this gentle guidance preserves continuity. Observational evidence shows that even in regions of past disturbance, thermal signatures fade smoothly, and the environment resumes equilibrium. Such resilience reflects a system designed by physical law to damp extremes and favor balance. Temperature measurements capture this resilience by revealing how energy spreads and settles rather than spikes and vanishes. This insight informs not only astrophysics, but also philosophy of observation, because it emphasizes patience and accumulation over immediacy. Knowledge of space temperature grows through long-term study and careful averaging rather than instant detection. This methodology aligns with the phenomena themselves, which unfold slowly and reward sustained attention. Temperature thus becomes a language of time, translating motion into history and potential. It matters because it encodes both past influence and future possibility within a single quiet measure. Understanding this encoding allows prediction without alarm and interpretation without urgency. The universe appears ordered not because it resists change, but because change is regulated and paced by thermal balance. Through this lens, space is not hostile or extreme, but measured and self-consistent. Temperature serves as one of its most reliable guides, maintaining coherence across vast distances and ensuring that evolution proceeds through steady adjustment rather than abrupt upheaval. This steady adjustment defines the character of the cosmos and invites continued observation within a framework of calm expectation and enduring balance. As perspective widens further, the significance of temperature becomes evident in how it links energy to time and stability across environments that appear empty, yet remain dynamically regulated. Temperature does not act independently, but reflects the cumulative outcome of countless interactions occurring slowly and quietly. And through this reflection, it encodes constraints that shape what can persist and how systems respond to change. In regions where energy input remains low and consistent matter settles into states that endure because radiative losses match gains over extended durations. This matching produces equilibrium that is not static but gently maintained through continuous exchange. When conditions drift, equilibrium shifts accordingly, and systems follow without overshoot or oscillation, illustrating a preference for gradual adjustment inherent in radiative processes. This behavior contrasts with dense environments where collisions rapidly redistribute energy and amplify fluctuations. The sparse character of space, therefore, favors smooth thermal evolution and suppresses volatility. This suppression has consequences for dynamics because it limits rapid expansion-contraction or phase change and allows trajectories to unfold predictably. Planetary debris rings provide an example where particles cool through radiation and maintain stable orbits while exchanging minimal energy with neighbors. Their temperatures reflect exposure and composition rather than crowding. Cometary bodies illustrate long-term thermal memory because their internal temperatures preserve records of distant formation environments and change only when exposed to sustained radiation near stars. Such preservation is possible because low collision rates and slow conduction protect internal states from rapid alteration. Temperature thus acts as an archive, preserving information across time. On intergalactic scales, this archival role extends to radiation fields whose spectra record expansion history and energy dilution. By reading these spectra, scientists reconstruct timelines without relying on transient markers. The calmness of thermal records enables confidence in inference because noise averages out and persistent signals remain. This reliability matters for models that seek coherence across scales and eras. Temperature gradients guide flows of matter and radiation without imposing abrupt direction, and these flows shape filaments, voids, and clusters through steady bias rather than force. The resulting structures appear ordered because the underlying thermal landscape changes slowly and uniformly. Where gradients steepen, local effects arise, but they dissipate as energy spreads thinly. This thin spreading is a defining feature of space, and it ensures that intense events integrate into the whole without destabilizing it. The moderation provided by temperature influences angular momentum, transport chemical kinetics, and phase stability in ways that favor continuity. Molecules survive long enough to interact, dust aggregates persist long enough to accrete, and clouds cool long enough to collapse. Each outcome depends on thermal pacing rather than intensity. The absence of rapid thermal equilibration also means that diversity can persist side by side because neighboring regions do not immediately homogenize. This coexistence supports complexity without competition and allows multiple pathways to unfold simultaneously. Observation confirms that boundaries between thermal regimes are broad and transitional rather than sharp, reinforcing the idea of gradients over thresholds. Temperature, therefore, serves as a quiet framework that organizes possibility space without dictating outcomes. It defines envelopes within which processes occur and timescales over which they unfold. Understanding these envelopes clarifies why the universe changes slowly yet continuously, and why stability emerges without rigidity. Through sustained radiative balance, temperature harmonizes energy distribution across vast distances, maintaining order while permitting evolution. This harmony is not imposed, but arises naturally from the physics of sparse interaction and pervasive radiation. Within this understanding, space appears as a system tuned for patience, where thermal regulation underwrites coherence and guides transformation through calm persistence. As consideration returns to the practical implications of thermal behavior, the relevance of space temperature becomes apparent in exploration, designed survival, and long-term presence beyond Earth. And these applications reflect the same calm principles observed at cosmic scales. In the absence of air, heat cannot be shed through convection, and conduction is limited to internal structures, so radiation becomes the sole pathway for energy exchange with the environment. Spacecraft therefore operate within a thermal reality governed entirely by surface properties, orientation, and exposure. Reflective coatings reduce absorption, while radiative panels emit excess energy, and rotation distributes heating evenly, preventing localized extremes. These strategies mirror the natural balance observed in space, where energy is neither trapped nor lost abruptly, but managed through steady emission. The success of long-duration missions depends on respecting this balance rather than attempting to resist cold or heat directly. Instruments must remain within narrow thermal ranges to function reliably, and this stability is achieved through gradual regulation rather than rapid correction. Planetary probes experience cycles of heating and cooling as they move through shadow and sunlight, and their design anticipates these cycles as predictable rhythms rather than hazards. Temperature thus becomes a scheduling factor guiding operation, timing data collection, and energy management. On human missions, thermal comfort and safety require insulation and controlled radiation exchange, because the surrounding environment offers no buffering medium. Spacesuits, habitats, and vehicles all incorporate layers that slow heat loss and manage emission in alignment with vacuum conditions. These measures rely on understanding that space itself does not impose cold through contact, but allows heat to escape if not retained. This distinction simplifies interpretation and informs efficient design. Beyond engineering, temperature influences navigation and observation, because thermal noise affects sensor sensitivity and background radiation sets detection limits. Cooling detectors improves resolution by reducing internal motion and aligning measurement conditions with ambient space temperatures. This alignment enhances clarity without altering the environment. Astronomical observatories exploit cold space to achieve stability because reduced thermal variation minimizes distortion and drift. This exploitation demonstrates how the coldness of space becomes an asset rather than an obstacle when understood correctly. On longer horizons, the thermal environment influences the feasibility of permanent structures, because materials must withstand slow radiation-driven change rather than rapid stress. Degradation occurs gradually, allowing monitoring and maintenance rather than sudden failure. This gradualism supports sustained presence and incremental expansion. Temperature, therefore, matters not as a threat, but as a parameter to be integrated calmly into planning and operation. By aligning technology with the natural pace of thermal exchange, exploration proceeds smoothly and predictably. This alignment reflects a broader principle that success in space comes from cooperation with physical law rather than opposition. Understanding temperature as a quiet regulator enables this cooperation and reduces uncertainty. It allows confidence that systems will behave consistently over time because energy flows remain stable and measurable. This confidence extends from individual components to mission architecture and long-term strategy. Through careful design informed by thermal principles, humanity engages with space in a manner that respects its calm structure. Temperature guides decisions without urgency, shaping pathways that unfold steadily and safely. Within this context, the real temperature of space is not an abstract concept, but a practical foundation supporting exploration continuity and sustained understanding. As attention settles on the quiet continuity of thermal influence, it becomes possible to recognize how temperature weaves together observation theory and experience into a single coherent understanding of space. Temperature operates not as a force but as a descriptor that reflects how energy is shared and how slowly that sharing occurs across sparse environments. This sharing is mediated by radiation that moves freely and evenly without preference and without interruption. When energy enters a region, it spreads outward through emission and scattering until balance is restored, and this restoration follows predictable paths shaped by physical law rather than chance. The absence of dense matter ensures that this spreading remains gentle, and that extremes dissolve into gradients rather than shocks. Even where intense sources exist, their influence fades smoothly with distance, preserving the overall calm. This calm allows patterns to persist long enough to be studied and understood, and it underlies the reliability of thermal models across scales. By treating temperature as an average property, scientists bridge the gap between microscopic motion and macroscopic behavior, and this bridge supports interpretation without relying on intuition. Intuition often associates cold with emptiness and heat with presence, yet in space, these associations dissolve because energy can be abundant without producing warmth, and absence of matter can coexist with constant radiation. Recognizing this separation clarifies why space environments feel conceptually counterintuitive, but remain physically consistent. Temperature measurements capture this consistency by revealing distributions that change slowly and uniformly over time. Long-term surveys show that despite local variation, the overall thermal structure of space remains stable, and this stability enables cumulative understanding. Cumulative understanding matters because it allows prediction without alarm and planning without haste. When future conditions are inferred, they follow from present trends rather than from sudden shifts. This predictability supports exploration science and interpretation alike, and it aligns with the broader character of cosmic evolution. Cosmic evolution proceeds through incremental adjustment guided by energy balance and moderated by expansion and radiation. Temperature traces this guidance quietly and faithfully. Within interstellar clouds, slow cooling enables chemistry to progress step by step, while within diffuse regions, low temperatures preserve states over long durations. Neither outcome requires urgency, and neither invites disruption. The same principles apply near planets, stars, and galaxies, where confinement modifies energy exchange, but does not alter its fundamental pacing. Thermal gradients appear where structure exists, and they relax where openness prevails. This relaxation is key because it prevents accumulation of instability and ensures that systems return to equilibrium after disturbance. Such resilience emerges naturally from radiative processes that favor distribution over concentration. Observation confirms that after energetic events, environments cool predictably and integrate smoothly into their surroundings. The universe therefore maintains coherence not by resisting change, but by regulating its tempo. Temperature sets that tempo by defining how quickly energy can move and how slowly systems respond. Understanding this role reframes the question of why temperature matters by shifting focus from sensation to regulation. It matters because it determines timescale rather than intensity, and because timescale governs possibility. Processes that require time depend on thermal moderation to unfold, and processes that unfold too quickly are damped by energy dispersion. This balance fosters diversity without chaos and persistence without rigidity. Across all regions, space exhibits this balance through steady thermal behavior that supports long-lived structures and gradual transformation. When viewed in this light, the real temperature of space emerges as a quiet but essential feature that underlies every motion, interaction, and evolution. It matters because it encodes the rules by which energy flows, and because those rules ensure that the universe remains intelligible, stable, and calm across distances that exceed direct experience. Through patient observation and careful interpretation, temperature reveals itself as a continuous guide, shaping the cosmos without drawing attention and without urgency. As the narrative approaches a broader synthesis, the meaning of temperature in space can be understood as a steady mediator between energy presence and energy effect, and this mediation remains consistent across all examined scales. Temperature does not announce itself through sensation, but through consequence, because it determines rates, limits, and balances that quietly shape outcomes over time. By constraining how quickly particles exchange energy, temperature governs whether systems remain diffuse, condense gradually, or maintain long-term stability. In the sparsest regions, this governance is subtle because interactions are rare and radiation dominates. And yet even here the influence persists through the background field that provides a universal reference. This reference ensures that no system exists without context, and that isolation still implies participation in a larger thermal framework. When matter absorbs energy, it responds by increasing motion, and when it emits energy, it relaxes toward equilibrium, and these responses unfold smoothly without oscillation. The absence of frequent collisions prevents amplification of fluctuation and favors monotonic adjustment toward balance. This monotonic behavior underlies the calm character of space and allows thermal states to be described reliably without needing rapid correction. Temperature thus serves as a stabilizer not by enforcing uniformity, but by limiting divergence. Where gradients arise, they spread and soften, and where energy concentrates, it disperses thinly across volume. This thinning is essential because it prevents localized conditions from overwhelming surrounding regions and preserves diversity across environments. Diversity persists because neighboring systems do not instantly homogenize, and this delay allows multiple states to coexist and evolve independently. Within this coexistence, complex pathways emerge guided by slow energy exchange rather than rapid mixing. Chemical networks develop within protected niches, gravitational structures grow, where cooling permits and radiation fields adjust without erasing contrast. Temperature sets the bounds within which these pathways remain viable, and these bounds shift predictably with distance, exposure, and time. As expansion continues on the largest scales, energy densities decline and average temperatures follow in a smooth trajectory that reflects conservation rather than depletion. Nothing is lost abruptly, and nothing appears without cause, and this continuity supports a coherent narrative of cosmic history. By tracing temperature changes, scientists reconstruct sequences of formation, transformation, and stabilization without relying on dramatic markers. The quietness of thermal evolution ensures that records persist and that interpretation remains grounded. Instruments designed to observe faint signals depend on this quietness, because reduced thermal noise enhances clarity and resolution. The coldness of space becomes a resource enabling precision rather than an obstacle imposing limitation. This inversion of expectation illustrates how understanding reframes challenge into advantage through alignment with physical law. Exploration, planning, observation, strategy, and theoretical modeling all benefit from treating temperature as a guide to pacing rather than a measure of severity. When pace is understood, processes can be anticipated and managed calmly. The absence of urgency reflects the absence of sudden thermal change, and this absence defines the operational reality of space. Across mission scales and epochs, temperature remains a constant consideration informing decisions without demanding reaction. It matters because it underlies the reliability of systems and the predictability of environments. As long as energy flows remain governed by radiation and sparse interaction, the universe will continue to evolve through gentle adjustment rather than abrupt transition. Temperature encapsulates this mode of evolution by summarizing how energy is shared and how slowly that sharing proceeds. Through this summary, a consistent picture emerges where space is not defined by extremes, but by regulation. This regulation enables order to persist across vast distances and long durations, and invites sustained observation without disturbance. Within this, understanding the real temperature of space stands as a foundational parameter shaping every context while remaining unobtrusive. It matters because it quietly determines the conditions under which everything else unfolds, and because it maintains a universe that changes through balance, patience, and continuity, rather than urgency or disruption. As the discussion moves toward an integrative understanding, temperature can be recognized as a boundary condition that frames every interaction without asserting itself as a direct agent, and this framing persists regardless of scale or location. Temperature does not drive motion, but it defines how motion is distributed and how rapidly systems respond to change. In doing so, it shapes the landscape within which physical processes operate, and it does so quietly through averages rather than extremes. In sparse environments where matter rarely meets matter, the averaging process becomes especially important because it allows description without relying on frequent interaction. Radiation provides the connective tissue that enables this averaging by linking distant systems through energy exchange that is continuous and gentle. When a system emits radiation, it participates in a wider equilibrium, and when it absorbs radiation, it adjusts incrementally rather than abruptly. This incremental adjustment favors stability and discourages runaway behavior because deviations are corrected slowly and evenly across time. Temperature, therefore, becomes a measure of participation in this shared radiative context rather than a local sensation. Across interstellar and intergalactic space, this shared context ensures coherence even as density declines and distances grow. Structures that form within this context inherit its pacing and evolve accordingly through gradual accumulation rather than rapid transformation. Cooling times lengthen, interactions slow, and processes that depend on patience become dominant. This dominance explains why large-scale structures endure and why dramatic change is rare outside confined regions. Confined regions such as stars and planets create their own thermal regimes through gravity and containment. Yet even these regimes release energy outward and rejoin the broader balance. The release is steady and moderated, ensuring continuity between the confined and the open. Observation confirms that temperature gradients around such structures relax smoothly and integrate into the background without shock. This integration preserves the calm character of space while allowing localized complexity. The importance of temperature lies in its ability to reconcile these two states' complexity and calm within a single framework. By governing rates rather than outcomes, temperature permits diversity without instability. In regions where temperatures are low, processes proceed slowly but reliably, and this reliability enables accumulation of change that would be impossible under rapid fluctuation. Molecules survive long enough to interact. Dust grains, aggregate, and gravitational potentials deepen over time. None of these require high-energy, only sustained conditions. Temperature provides those conditions by limiting the pace of energy redistribution. When energy input increases, the system responds by radiating more efficiently, restoring balance without overshoot. This feedback operates universally and underpins the predictability of thermal behavior. Predictive power matters because it allows modeling of future states based on present conditions without invoking sudden unknowns. Such modeling supports exploration and theory by aligning expectation with reality. As space continues to expand, average temperatures decline slowly and uniformly, preserving the same governing principles across epochs. This slow decline maintains continuity between past, present, and future, and allows understanding to extend across time. Temperature thus becomes a narrative thread connecting early dense conditions to the present sparse environment. It matters because it records the history of energy flow and defines the horizon of possibility. Within this narrative, space is revealed as an environment shaped by moderation, where extremes are localized and the whole remains balanced. Temperature ensures that balance by distributing energy thinly and evenly through radiation and sparse interaction. This distribution supports a universe that is intelligible, stable, and conducive to long-term structure. By appreciating temperature in this way, the apparent coldness of space transforms into an expression of order rather than absence. It reflects a system optimized for patience, where change unfolds through accumulation and equilibrium rather than force. Within such a system, observation, understanding, and presence can persist without urgency. Temperature quietly sustains this persistence, and in doing so, it matters profoundly as a foundational aspect of the cosmos that governs how energy becomes structure and how structure endures over time. As the exploration settles into its final layers, temperature can be appreciated as a condition that quietly shapes expectation rather than demanding attention, and this appreciation completes the gradual picture of how space maintains order without intervention. Temperature defines limits within which systems remain stable, and these limits are respected naturally because energy exchange proceeds slowly and evenly. When limits are approached, responses unfold through radiation and redistribution rather than through abrupt correction. This gentle response ensures continuity and prevents cascading change that would otherwise disrupt large-scale coherence. In this way, temperature acts as a moderator that integrates local variation into global balance. Environments may differ widely in exposure density and history, yet their thermal behavior remains interpretable within a shared framework. This shared framework allows comparison across scales and supports understanding that does not depend on proximity or sensation. The universe becomes legible through averages, trends, and gradients that persist over time. In sparse regions where interaction is minimal, temperature changes so slowly that states endure and memory is preserved. This preservation allows matter to carry traces of formation conditions across vast durations and distances. Scientists read these traces through radiation signatures and energy distributions, revealing histories encoded quietly in thermal state. Such encoding is reliable because it is not overwritten rapidly and because noise dissipates faster than signal. Temperature thus supports clarity by favoring long-term patterns over short-term fluctuation. Clarity matters because it enables cumulative knowledge and confidence in inference. Without stable thermal baselines, interpretation would fragment and prediction would lose grounding. The calmness of space temperature therefore underwrites the coherence of scientific understanding itself. As models incorporate thermal regulation, they align more closely with observation and yield insights that remain robust across contexts. This robustness reflects the universality of radiative processes and sparse interaction. No region escapes these principles, and none requires special exception. Even in extreme environments, the same logic applies, though parameters shift. This consistency reinforces the idea that space operates through steady law rather than episodic behavior. Temperature embodies this steadiness by summarizing how energy is shared and how quickly change can occur. It matters because it governs tempo, and tempo governs possibility. Slow tempos allow accumulation, reflection, and persistence, while fast tempos limit duration and amplify instability. The cosmos favors the former across most of its volume, and temperature is the mechanism that enforces this preference. Through gradual cooling, expansion, and radiation balance, the universe sustains a pace that supports structure, diversity, and longevity. Planets, stars, and galaxies arise within this paced environment and endure because energy exchange remains moderated. Beyond them, the surrounding space maintains a background that absorbs influence without upheaval. This absorption protects coherence and ensures that change remains local rather than systemic. Understanding this relationship clarifies why the coldness of space is not hostile but supportive. It provides a stable stage upon which confined warmth can exist without spreading uncontrollably. This balance between cold openness and warm structure defines the architecture of the universe. Temperature sits at the center of this architecture, not as a visible pillar, but as a governing condition. Its influence is subtle yet pervasive, shaping outcomes without announcing cause. By recognizing temperature in this role, the universe can be seen as an environment optimized for calm evolution, where energy flows guide form gently and predictably. This recognition completes the narrative by revealing why the real temperature of space matters beyond description. It matters because it sustains order across scale, maintains continuity across time, and allows complexity to arise without disturbance. Through patient regulation and steady exchange, temperature ensures that the cosmos remains intelligible, enduring, and quietly balanced as it continues its long unfolding without urgency or interruption. As the narrative continues, temperature can also be understood as a contextual signal that informs interpretation rather than commanding reaction, and this role reinforces the calm structure observed throughout space. When scientists encounter new environments, they evaluate thermal conditions to determine expected behavior and stability. Low temperatures suggest slow chemistry and long persistence, while higher temperatures indicate faster motion and increased interaction. These expectations guide observation planning and theoretical framing without imposing urgency. Temperature thus functions as an orienting parameter that quietly narrows the range of plausible outcomes. In environments dominated by radiation, balance changes occur through gradual adjustment, and this predictability allows confidence in long-term projections. Systems exposed to steady conditions respond steadily, and deviations relax over time rather than escalate. This relaxation is visible in how thermal anomalies dissipate and merge into surrounding gradients. Such behavior supports the idea that space favors integration over isolation and balance over extremes. Even where boundaries exist, they are broad and transitional, allowing influence to fade gently rather than stop abruptly. This gentleness preserves continuity and avoids sharp contrasts that could destabilize adjacent regions. The thermal landscape therefore resembles a smooth field where variations are expressed as slopes rather than cliffs. Within this field, motion proceeds along paths defined by energy availability and resistance imposed by sparse interaction. Matter follows these paths without haste, guided by gradients that are shallow and persistent. The absence of abrupt thermal barriers allows trajectories to extend across large distances and durations without interruption. This openness supports the mixing of histories and the sharing of influence without forcing convergence. Temperature sets the pace at which such sharing occurs, ensuring that diversity remains while coherence is maintained. Observation of these processes reveals a universe that resolves differences through diffusion and radiation rather than collision and shock. This resolution operates quietly and continuously, reinforcing stability across scale. By appreciating temperature as a field rather than a point, property interpretation becomes more fluid and less prone to contradiction. Environments that appear cold or warm are understood as positions within a broader distribution rather than as isolated states. This understanding dissolves apparent paradoxes and aligns description with physical reality. Temperature measurements gain meaning when placed within this context because they describe position within a gradient rather than absolute condition. This relational view matters because it connects local observation to global structure. Through its small-scale findings, inform large-scale models and vice versa without conflict. The universe appears ordered because these relationships remain consistent and because energy redistribution follows predictable pathways. Temperature anchors these pathways by defining how quickly adjustment occurs and how far influence extends. Its quiet guidance ensures that no region evolves in isolation from the whole. Over time, this interconnectedness produces patterns that are robust and enduring. Galaxies maintain structure, voids remain sparse, and radiation fields persist uniformly. Temperature underlies each of these outcomes by moderating exchange and pacing evolution. In recognizing this moderation, the role of temperature becomes clear as a unifying influence that harmonizes motion without directing it. It matters because it shapes expectation, interpretation, and possibility through steady constraint rather than force. Within this framework, space is revealed as a system governed by gentle regulation, where understanding deepens through patience and observation rather than reaction. Temperature sustains this system by maintaining balance across time and distance, and by ensuring that change unfolds as a continuous flow rather than a series of disruptions. As the perspective settles into a state of continuity, temperature can finally be regarded as an environmental constant that provides reassurance through predictability rather than challenge through extremity. And this perspective completes the calm, scientific understanding of space. Temperature does not demand attention because it rarely changes quickly, and this slowness allows systems to adapt without strain. Adaptation in space occurs through alignment with prevailing energy conditions rather than resistance, and this alignment minimizes stress on matter and structure. When environments cool or warm, the transition unfolds across long durations, giving time for redistribution and adjustment. This extended timescale prevents abrupt failure and supports endurance across cosmic history. Objects exposed to space gradually find equilibrium states where energy input and loss remain balanced, and once reached, these states persist until conditions shift measurably. Persistence is therefore the norm rather than the exception, and temperature is the mechanism that enforces this norm. By limiting how fast energy can accumulate or dissipate, temperature ensures that matter remains within survivable bounds. This limitation is not restrictive but enabling, because it provides a stable framework within which complexity can arise and remain coherent. Without such limitation, systems would fluctuate too rapidly for structure to hold. The universe demonstrates that moderation is not weakness but strength, and temperature embodies this principle at every level. From isolated dust grains to galactic clusters, thermal regulation maintains form through patience. Observational records confirm that even over billions of years, average temperatures shift smoothly rather than erratically, and this smoothness underpins confidence in long-term modeling. Models that incorporate thermal pacing align with evidence because they respect the same constraints that govern reality. This alignment allows prediction without alarm and exploration without haste. When planning future observation or presence in space, temperature informs design timelines and expectations, ensuring that systems are prepared for gradual change rather than sudden extremes. This preparation reduces risk and supports continuity of operation. Beyond practical application, temperature influences interpretation by framing what is plausible within a given environment. Cold regions suggest longevity and preservation, while warmer regions suggest activity and transformation, and these interpretations guide focus without bias. The absence of emotional charge in thermal description reinforces objectivity and allows understanding to remain grounded. Temperature thus becomes a language of moderation, communicating conditions through balance rather than intensity. This language applies universally because the same principles govern all regions regardless of scale. The universality of thermal behavior strengthens the coherence of physical law and supports the idea of a unified cosmos. By observing how temperature behaves, scientists see consistency rather than contradiction, and this consistency fosters trust in explanation. Over time, as exploration extends farther, the same patterns reappear, confirming that space remains governed by calm regulation. The role of temperature in this regulation is subtle yet comprehensive, shaping motion, interaction, and stability without drawing focus. It matters because it quietly defines the environment in which all other processes occur, and because it ensures that change remains intelligible and measured. Through steady energy exchange and gradual adjustment, temperature preserves continuity across distances that exceed direct experience. This preservation allows the universe to be understood as an ordered system rather than a collection of extremes. Within this ordered system, temperature stands as a silent organizer, maintaining equilibrium and pacing evolution through patience. By acknowledging this role, the narrative of space shifts from one of harshness to one of balance, where cold and energy coexist through law rather than conflict. Temperature sustains this balance continuously and without urgency, and in doing so it matters as one of the most fundamental conditions shaping the long and quiet unfolding of the universe. As the final connections emerge, temperature can be seen as a steady reference that aligns observation, expectation, and outcome across environments that differ widely yet remain governed by the same principles. This reference does not impose direction, but provides boundaries within which processes unfold predictably. By defining how quickly energy can move, temperature sets the cadence of interaction, and this cadence favors continuity over disruption. In space where radiation dominates exchange, this cadence is slow and even allowing systems to remain near equilibrium for long durations. Near sources of energy gradients appear, yet they relax smoothly with distance and time, preserving coherence across regions. This smooth relaxation explains why contrasts coexist without instability, and why localized warmth does not propagate uncontrollably into the surrounding cold. The surrounding cold absorbs influence thinly and disperses it through radiation, maintaining balance. Temperature thus acts as a mediator that reconciles presence of energy with persistence of calm. Within this mediation, histories are preserved because rapid overwriting is unlikely and signals accumulate rather than vanish. Accumulated signals enable reconstruction of formation conditions, trajectories, and timelines through careful analysis. This capability matters because it transforms observation into understanding without reliance on fleeting events. The thermal record remains legible precisely because change is paced. Legibility supports confidence in models that extend beyond immediate measurement and allows inference across scales. When applied to planetary systems, temperature clarifies why atmospheres endure, evolve, or dissipate gradually rather than suddenly. Retention depends on the balance between heating and radiative loss, and this balance shifts slowly under stable conditions. When applied to stellar systems, temperature explains how energy generated in confined cores is released, gently shaping surroundings without erasing structure. When applied to interstellar and intergalactic media, temperature reveals why vast volumes remain cold yet active, and why matter persists between events. Across all these contexts, the same quiet logic holds. Energy is present, energy moves, and energy settles, and temperature tracks this movement without dramatization. By recognizing temperature as a summary of distribution, rather than a trigger of sensation, confusion dissolves and interpretation stabilizes. The universe appears neither hostile nor inert, but regulated and patient. This patience underwrites the possibility of long-term structure, because systems are granted time to adjust and respond. Time allows complexity to emerge through accumulation rather than through intensity. Chemical networks form, dust aggregates coalesce, and gravitational patterns deepen under conditions that favor endurance. Temperature is the condition that grants this endurance by limiting pace. Without such limitation, processes would outrun stability and coherence would fail. The consistent presence of a thermal baseline ensures that no region escapes context and that extremes remain localized. This assurance allows exploration and theory to proceed without urgency because outcomes are bounded and change is foreseeable. Temperature therefore matters as a foundation for expectation and planning. It informs where attention may be rewarded and where patience is required. Through steady radiative exchange and sparse interaction, it maintains an environment where knowledge can grow cumulatively. This cumulative growth mirrors the environment itself, where energy redistribution is continuous and measured. As the cosmos continues its expansion, the same principles persist, and temperature continues to decline smoothly, without altering the governing logic. The future remains intelligible because the rules remain constant. In this constancy, temperature stands as a quiet guarantor of order, guiding evolution through balance rather than force. It matters because it sustains a universe that can be understood, inhabited, and observed over long durations without disruption. Within this sustained order, the real temperature of space is revealed not as an extreme, but as a stabilizing presence that frames all motion and change through calm regulation and enduring equilibrium. As the closing phase of reflection approaches, temperature can be understood as the quiet condition that allows all other variables to remain meaningful. And this understanding draws together observation, theory, and application into a single calm framework. Temperature does not dominate narratives of space because it rarely changes quickly, and this restraint allows other processes to be interpreted against a stable background. Stability enables comparison, and comparison enables understanding across distance and time. When environments are stable, measurements accumulate, and patterns become visible, and these patterns persist long enough to be distinguished from noise. Temperature provides the stability that supports this accumulation by moderating how energy enters, leaves, and redistributes within systems. In sparse regions, radiation exchange sets a slow rhythm that discourages abrupt transitions and encourages equilibrium. This equilibrium is dynamic rather than static because energy continues to flow, yet the flow remains balanced. Balanced flow prevents extremes from spreading and confines rapid change to regions where containment exists. The surrounding openness absorbs influence without resistance, dispersing energy thinly and restoring calm. This dispersal is essential for maintaining coherence because it ensures that local events integrate into the whole without altering global conditions. Temperature therefore serves as a connective property linking local behavior to universal structure. It defines how far influence extends and how long effects endure. Through this definition, systems remain predictable and models remain applicable across contexts. Predictability matters because it reduces uncertainty and allows planning that aligns with physical reality rather than reacting to perceived threat. Exploration science and habitation all rely on this predictability because survival and success depend on gradual adjustment rather than rapid response. Temperature informs material choice, operational pacing, and observational strategy through its steady guidance. Beyond utility, it informs perspective by revealing that space is not defined by hostility, but by moderation. Coldness is not an absence, but a consequence of thin distribution and slow exchange. Recognizing this consequence reframes emptiness as a condition of balance rather than lack. Balance supports endurance, and endurance supports complexity. The universe demonstrates that complexity arises not from intensity, but from sustained conditions that allow accumulation over time. Temperature underwrites these conditions by limiting how fast energy can disrupt order. When energy input increases, temperature rises locally, but radiation carries excess away, restoring balance without collapse. This self-correcting behavior appears consistently across scales, reinforcing confidence in physical law. Confidence allows inquiry to proceed without urgency, because outcomes remain bounded. The role of temperature in this bounding is subtle yet decisive. It sets envelopes rather than trajectories, and within these envelopes diverse paths unfold. Diversity persists because envelopes overlap without forcing uniformity. This overlapping allows neighboring systems to differ while remaining connected. Temperature gradients bridge differences gently and ensure continuity. Through these gradients, motion remains smooth and histories remain legible. Legibility enables reconstruction, and reconstruction deepens understanding. As understanding deepens, the apparent simplicity of temperature reveals profound influence. It matters because it quietly shapes possibility, pace, and persistence across the cosmos. By governing energy flow without imposing direction, temperature sustains a universe that evolves through calm adjustment. This adjustment allows order to endure and change to occur without disruption. Within this enduring order, space becomes a domain where observation can continue, reflection can deepen, and presence can be sustained. Temperature remains the silent condition that makes all of this possible, and in remaining silent, it fulfills its role, perfectly maintaining balance, continuity, and intelligibility across the vast expanse without urgency or disturbance. As the narrative settles into its final moments, temperature stands revealed as a background condition that quietly supports coherence rather than seeking emphasis. And this perspective completes the calm scientific arc without introducing finality. Temperature remains active yet unobtrusive, guiding processes through limitation rather than instruction. By defining how energy disperses, it determines which arrangements endure and which dissolve over time. This determination unfolds slowly and evenly because radiative exchange favors gradual redistribution and discourages accumulation beyond sustainable bounds. The resulting environment allows matter to occupy stable configurations for long durations, and this stability underpins the persistence of structure across cosmic history. Stars, planets, clouds, and diffuse regions all participate in this shared thermal context, even as they express it differently. Differences arise from containment, density, and exposure, yet the governing logic remains the same. When containment is strong, energy can accumulate and temperatures rise, while when openness prevails, energy spreads thinly and temperatures remain low. This duality coexists peacefully because transitions are smooth and reversible. Temperature gradients mediate between states, allowing influence to fade rather than collide. Through this mediation, the universe avoids sharp discontinuities and preserves intelligibility across scale. Intelligibility matters because it allows understanding to accumulate without contradiction. Observations made in one context remain applicable in others because thermal behavior follows consistent rules. This consistency supports trust in inference and confidence in long-term projection. As expansion continues and densities decline, the same principles guide evolution toward new equilibria without altering the foundational framework. Temperature continues to decline gradually, yet its role as regulator remains unchanged. Processes slow further, and persistence becomes even more pronounced. The universe thus moves toward states defined by patience and endurance, rather than by rapid transformation. Within these states, energy flows continue quietly, maintaining balance without drawing attention. The absence of urgency in thermal behavior mirrors the absence of urgency in cosmic evolution as a whole. Change occurs, but it is measured and predictable, allowing systems to adjust without stress. This measured change is what allows complexity to exist alongside simplicity without conflict. Complex structures emerge within confined regions, while vast spaces remain sparse and calm. Temperature enables this coexistence by regulating energy exchange between regions without forcing uniformity. In doing so, it maintains diversity while preserving unity. This balance between diversity and unity defines the architecture of the cosmos, and temperature is central to sustaining it. By limiting pace, temperature grants time, and time grants opportunity for structure to form, persist, and be understood. Understanding grows through sustained observation, and temperature ensures that conditions remain stable enough for such observation to be meaningful. The scientific study of space relies on this stability because it allows faint signals to be distinguished from noise and long-term trends to be identified. Without thermal moderation, observation would be overwhelmed by fluctuation. Temperature therefore matters because it underwrites the possibility of knowledge itself. It ensures that the universe can be read, interpreted, and modeled through calm accumulation rather than reactive response. As this understanding settles, the real temperature of space emerges not as an extreme value, but as a stabilizing influence that frames every interaction quietly and consistently. It matters because it sustains a universe where energy flows do not disrupt order, but instead maintain it through balance. Within this sustained balance, the cosmos continues its long unfolding, guided by law rather than impulse, and by regulation rather than force. Temperature remains the silent companion of this unfolding, ensuring that change remains intelligible, enduring, and calm across the vast reaches of space. As continuity carries forward, temperature can finally be regarded as an interpretive baseline that steadies perception and supports coherence across every environment encountered. And this baseline operates without assertion, guiding understanding through quiet consistency. Temperature offers a common scale by which disparate regions can be compared, And this comparability matters because it links isolated observations into a unified picture. Without such linkage, data would remain fragmented, and meaning would be local rather than cumulative. In space, where distances are immense and interactions are sparse, cumulative meaning depends on properties that change slowly, and temperature is one such property. Its slow variation allows signals to be integrated over time, revealing patterns that would otherwise be obscured by immediacy. Radiative processes ensure that energy exchange remains continuous and distributed, and this distribution smooths variation into gradients that can be followed and interpreted. Gradients provide direction without force, allowing matter and radiation to respond naturally rather than reactively. This natural response underlies the calm progression of cosmic systems because adjustments occur through alignment rather than opposition. When energy increases, locally temperature rises and radiation carries excess away, restoring balance without shock. When energy decreases, temperature falls and absorption from the background moderates decline. These paired tendencies form a feedback loop that favors stability and discourages extremes. The loop operates universally and does not require intervention because it arises from the fundamental nature of radiation and sparse interaction. Understanding this loop clarifies why the universe appears resilient despite hosting energetic events. Resilience is not accidental, but a consequence of thermal moderation that integrates change into continuity. Observational records spanning long durations show that even after disturbances, environments return to predictable states, and this return validates models grounded in thermal balance. Validation builds confidence, and confidence allows exploration and theory to advance without urgency. Temperature thus supports not only physical stability but epistemic stability, because it ensures that knowledge remains applicable over time. When conditions are stable, interpretations endure and learning accumulates. This accumulation enables deeper insight into processes that operate slowly and rewards patience in observation. Patience aligns with the environment itself, where meaningful change unfolds over long spans. By mirroring this pace, scientific practice becomes attuned to reality rather than driven by expectation. Temperature serves as a metronome, setting the rhythm of both physical evolution and understanding. Its rhythm is slow and even allowing synchronization across scales. From particle distributions to galactic structures, the same cadence applies, guiding interaction without compulsion. This guidance preserves diversity because systems are free to evolve within bounds rather than being forced toward uniformity. Bounds define possibility without prescribing outcome, and temperature defines these bounds through energy distribution. Within them, matter organizes, reorganizes, and persists according to local conditions while remaining connected to the whole. The connection is maintained through radiation that links all regions regardless of distance. This linkage ensures that no system is truly isolated and that equilibrium remains a shared reference. Equilibrium in this sense is dynamic and accommodating rather than static and rigid. It allows fluctuation within limits and change within continuity. Temperature encodes these limits gently and continuously. It matters because it translates the abstract concept of energy into a practical measure of pace and stability. Through it, the universe becomes readable as a system where cause and effect unfold without haste. As exploration extends and observation deepens, the same thermal logic continues to apply, reinforcing coherence across new contexts. The enduring applicability of this logic demonstrates that temperature is not merely a descriptive parameter, but a foundational organizer. It shapes how energy becomes structure and how structure endures. Within this shaping, the cosmos maintains a balance that invites sustained attention rather than urgent reaction. Temperature sustains this invitation by ensuring that change remains intelligible and that extremes remain contained. In fulfilling this role, temperature quietly underpins the long unfolding of space, guiding motion, interaction, and evolution through steady regulation and calm persistence across distances that challenge comprehension yet remain governed by the same gentle rules. As the sequence continues toward its concluding perspective, temperature may be regarded as the final unifying context that allows all other properties of space to be interpreted without contradiction. And this context remains steady even as conditions vary widely across distance and time. Temperature does not compete with other forces, but frames their effects by defining how energy is expressed collectively rather than individually. This framing ensures that motion, radiation, and structure can be compared meaningfully, even when environments differ dramatically. In the absence of dense matter, energy does not concentrate easily, and temperature remains low on average while still permitting localized intensity. This separation allows energetic processes to occur without destabilizing their surroundings, and it preserves the calm character of the larger environment. When matter becomes confined, gravity enables heating and temperature rises, yet radiation carries this energy outward, gradually integrating it into the wider context. Integration prevents isolation and ensures continuity between regions of activity and regions of stillness. This continuity is essential for coherence, because it prevents the universe from fragmenting into incompatible states. Temperature, therefore, serves as a translator between local behavior and global order. By averaging motion, it renders complex interactions intelligible and comparable across scale. This intelligibility supports long-term modeling because conditions do not change unpredictably, but follow trends governed by energy balance. Trends reveal direction without urgency and allow anticipation without alarm. Such anticipation underlies exploration, planning, theoretical development, and sustained observation. When expectations align with gradual change, confidence replaces reaction and inquiry proceeds calmly. The thermal environment of space fosters this calm, because it resists rapid redistribution and dampens extremes. Damping does not eliminate variation, but moderates it, ensuring that no single event dominates the whole. This moderation allows histories to accumulate and be read through radiation signatures and energy distributions. Reading these signatures provides insight into formation, processes, timelines, and evolutionary pathways. Temperature encodes these insights quietly because it changes slowly and preserves memory. Memory, in this sense, refers to retained conditions that inform present behavior. Dust grains retain thermal histories, gases preserve excitation states, and radiation fields record expansion. All of these depend on temperature stability to remain legible. Legibility matters because it allows reconstruction of events that occurred long before observation. Reconstruction extends understanding beyond immediate perception and connects present measurement to past reality. Temperature thus becomes a bridge across time as well as space. Its gradual evolution links epochs without erasing distinction. As the universe continues to expand and cool, this linking persists because the governing principles remain unchanged. Expansion alters scale but not logic, and temperature follows accordingly. The future thermal state will reflect the same balance of radiation dilution and sparse interaction seen today. This predictability reassures that understanding built now will remain applicable. Temperature, therefore, underwrites not only present interpretation but future comprehension. It matters because it provides a stable backdrop against which change can be recognized rather than lost. Within this backdrop, the universe unfolds through measured transitions rather than abrupt breaks. Structures arise, persist, and fade within envelopes defined by thermal balance. These envelopes allow coexistence of calm and activity without conflict. By maintaining these envelopes, temperature ensures that space remains an environment where order emerges naturally and endures quietly. The absence of urgency in thermal behavior mirrors the absence of urgency in cosmic evolution as a whole. Both favor patience, accumulation, and continuity. In this alignment, the real temperature of space reveals its deepest significance not as a number or sensation, but as a governing condition that sustains coherence across immensity. It matters because it keeps the universe intelligible, stable, and open to understanding over durations that far exceed individual moments. Through steady regulation and gentle energy flow, temperature supports a cosmos that evolves without haste and invites observation without disturbance, continuing its long unfolding guided by balance rather than impulse. As the narrative approaches its closing, equilibrium temperature emerges as the quiet boundary that ensures the universe remains interpretable rather than overwhelming. And this boundary holds steady across environments that differ widely in form and activity. Temperature does not assert direction, but delineates the range within which motion and interaction can occur, and by doing so it preserves coherence across scale. Energy may be present in many forms, yet its collective expression remains moderated through radiation and sparse interaction. This moderation prevents abrupt redistribution and allows systems to remain near balance for extended periods. Near sources of energy, local increases arise, but they dissipate smoothly into the surrounding field, restoring continuity. This smooth dissipation ensures that no region becomes isolated from the larger context, and that local histories integrate into global structure. Integration matters because it allows understanding to scale without contradiction. Observations made in confined systems remain consistent with those made in open regions because the same thermal principles apply. Temperature thus serves as a universal constraint that links micro and macro descriptions into a single framework. Within this framework, cause and effect unfold at a pace that favors clarity rather than surprise. Clarity supports accumulation of knowledge because patterns persist long enough to be recognized and confirmed. Persistence depends on the slow nature of thermal exchange, which dampens noise and emphasizes signal. Radiation acts as the carrier of this exchange, distributing energy thinly and evenly across distance. The thinness of distribution preserves gradients without creating shocks and allows structures to exist alongside voids. This coexistence defines the architecture of the cosmos, where complexity is localized and calmness prevails broadly. Temperature maintains this architecture by regulating the flow of energy between regions without enforcing uniformity. Regulation without uniformity allows diversity to persist and evolve independently within shared bounds. These bounds shift slowly with expansion and energy production, but their governing logic remains constant. As expansion proceeds, densities decline and average temperatures fall, yet the same mechanisms guide evolution toward new equilibria. The future, therefore, mirrors the past in principle, even as scale changes. Temperature encodes this mirroring by tracking energy dilution and exchange across time. Its gradual evolution ensures that transitions remain intelligible and that no phase change occurs without context. Context is preserved because temperature changes slowly and records prior conditions within present state. This recording enables reconstruction and interpretation without speculation. Measurement confirms that thermal trends follow predictable paths, validating models that emphasize balance and moderation. Validation reinforces confidence that the universe operates through steady law rather than episodic anomaly. This confidence allows inquiry to proceed without urgency, because outcomes remain bounded and comprehensible. Temperature supports this posture by maintaining a stable background against which variation can be assessed. Variation appears meaningful only because the background remains calm. In the absence of such calm, variation would blur into noise and understanding would falter. Temperature thus underpins intelligibility by stabilizing the reference frame of observation. It matters because it defines the environment in which meaning emerges and persists. Through steady regulation of energy flow, it sustains a universe that evolves through accumulation rather than disruption. This accumulation allows structures to form, histories to be read, and knowledge to deepen across time. Within this sustained order, the real temperature of space fulfills its role as a silent organizer, maintaining balance, coherence, and continuity, without demanding attention or urgency, as the cosmos continues its long and patient unfolding. As the final sense of continuity settles, temperature can be understood as the background agreement that all regions of space implicitly follow, and this agreement ensures that differences coexist without contradiction. Temperature provides a shared context that allows diverse environments to be compared, interpreted, and integrated into a single coherent picture. Without this shared context, observations would remain isolated and understanding would fragment across scale. In space, where direct interaction is rare, this shared context becomes especially important because it replaces contact with consistency. Radiation carries energy, information, and balance across distances, and temperature summarizes the outcome of this exchange without emphasizing individual events. This summary allows patterns to emerge over long durations, revealing steady trends rather than momentary fluctuations. Steady trends are essential for recognizing order because they persist beyond noise and distraction. Temperature stabilizes these trends by limiting how quickly energy can accumulate or dissipate. When accumulation is slow, systems have time to respond, adjust, and settle into configurations that endure. Endurance supports structure because gravity, chemistry, and aggregation require sustained conditions to operate effectively. In contrast, rapid thermal change would erase progress before it could consolidate. The universe avoids this outcome through the inherent moderation imposed by sparse interaction and radiative exchange. Moderation ensures that extremes remain localized and transient, while the broader environment retains balance. This balance is not imposed externally, but arises naturally from the physics of energy distribution. Temperature encodes this physics quietly by reflecting how evenly energy is spread and how slowly it moves. By doing so, it informs expectation without dictating outcome. Systems remain free to evolve along multiple pathways within bounds defined by thermal state. These bounds shift gently with expansion and energy production, allowing adaptation without disruption. Observation confirms that boundaries between thermal regimes are broad, transitional, and forgiving rather than sharp and exclusive. This forgiveness allows influence to fade gradually and prevents instability at interfaces. The result is a universe where regions blend rather than collide, and where change integrates rather than fractures. Temperature is central to this blending because it governs the rate at which differences equalize. Slow equalization preserves contrast while preventing runaway divergence. Contrast allows diversity, and diversity enriches structure. Thus, temperature indirectly supports complexity by pacing homogenization. Complexity emerges where conditions persist long enough for accumulation, and this persistence is a gift of thermal moderation. The same principle applies to understanding because Insights accumulate when conditions remain stable and temperature ensures such stability across observation periods. Long-term measurements gain meaning because baselines do not drift rapidly. This stability underwrites confidence in inference and allows models to extend across time. As exploration advances, the same thermal logic will apply in new contexts, reaffirming coherence. Temperature, therefore, matters as a guarantor of continuity linking past, present, and future through consistent behavior. It maintains a universe that is readable, predictable, and open to sustained inquiry. Within this universe, energy flows without urgency, matter organizes without compulsion, and change unfolds without rupture. Temperature supports this mode of existence by quietly regulating exchange and preserving balance. In fulfilling this role, it remains largely unnoticed, yet indispensable. The real temperature of space is not defined by sensation or extremity, but by its capacity to sustain order through patience. It matters because it keeps the cosmos intelligible and stable, allowing evolution to proceed as a long, calm narrative rather than a sequence of shocks. Through steady regulation and gradual exchange, temperature holds the universe together as a coherent whole and enables understanding to deepen without disturbance as time continues its unhurried progression. As the sense of completion draws nearer, temperature can be appreciated as the quiet condition that allows all previous insights to remain connected rather than isolated, and this appreciation reinforces the calm coherence of the whole narrative. Temperature does not resolve into a final statement because it functions continuously rather than conclusively. Its influence persists as long as energy moves and matter responds. In space, this persistence is evident because radiative exchange never ceases and sparse interaction never accelerates beyond moderation. The environment, therefore, remains governed by the same steady principles regardless of era or location. This steadiness allows understanding to remain relevant over time because foundational behavior does not shift abruptly. Observations made today remain meaningful tomorrow because thermal trends evolve slowly and predictably. Temperature thus anchors interpretation by providing a stable reference that resists rapid change. This resistance is not rigidity, but pacing, and pacing allows systems to adapt gracefully. Adaptation in space unfolds through gradual redistribution rather than through reaction, and this mode supports endurance across cosmic history. Stars exhaust fuel, planets cool, clouds condense and disperse, yet each transition follows paths defined by thermal balance. Balance ensures that change integrates rather than disrupts, and that continuity is preserved even as forms evolve. This preservation is essential for coherence, because it allows the universe to be understood as a single system rather than a series of disconnected episodes. Temperature unifies these episodes by encoding how energy is shared across time and space. Its encoding is subtle because it relies on averages and distributions rather than on dramatic events. Subtlety ensures that information is not overwritten quickly and that records persist. Persistent records enable reconstruction of past states and anticipation of future trends without speculation. Anticipation grounded in thermal behavior remains reliable because the same constraints apply universally. No region escapes radiative exchange, and no system accelerates beyond the limits set by sparse interaction. These universal constraints foster trust in explanation and reduce uncertainty. As a result, inquiry can proceed calmly without urgency because outcomes remain bounded and intelligible. Temperature supports this calm inquiry by maintaining stability across observational scales. It ensures that local variation does not obscure global pattern and that extremes remain contextual rather than dominant. Through this contextualization, understanding deepens and complexity becomes manageable. The universe appears vast yet orderly because temperature mediates between energy and effect continuously. Its mediation allows energetic processes to exist without overwhelming their surroundings, and allows cold regions to persist without stagnation. This coexistence defines the character of space as balanced rather than extreme. Temperature makes this balance possible by pacing exchange and preserving gradients. Gradients guide motion gently and ensure that transitions remain smooth. Smooth transitions allow structures to endure long enough to be studied, inhabited, and understood. Without such endurance, knowledge would fragment and exploration would lack foundation. Temperature, therefore, matters as the silent condition that sustains intelligibility across the cosmos. It enables a universe where change unfolds through accumulation and balance, rather than through abrupt transformation. Within this universe, observation aligns with reality, understanding aligns with law, and presence aligns with possibility. Temperature quietly maintains this alignment by regulating energy flow without asserting control. In doing so, it fulfills its role as a foundational aspect of space, shaping every process while remaining unobtrusive. The real temperature of space is thus revealed not as a single value, but as an enduring framework that supports coherent stability and calm evolution across immeasurable distances and times, continuing its subtle influence without conclusion or interruption. As the reflection extends into its final coherence, temperature can be recognized as the condition that allows the universe to remain comprehensible across scales without requiring intervention or urgency, and this recognition settles the narrative into a stable frame. Temperature does not announce presence through sensation, but through regulation, and this regulation is expressed through limits rather than commands. By setting boundaries on energy exchange, temperature ensures that processes unfold within predictable ranges and at manageable speeds. This predictability supports continuity, because systems do not exceed conditions that would erase structure faster than it can form. In sparse space where collisions are rare, radiation provides the only mechanism for redistribution, and radiation operates gently, spreading energy thinly and evenly across vast volumes. This spreading favors equilibrium and dampens extremes without eliminating variation. Variation remains localized and contextual, while the broader environment retains balance. Temperature encodes this balance by summarizing how energy is shared rather than how it is produced. Production may be intense within confined regions, yet distribution remains moderated once energy leaves containment. This moderation integrates local activity into global calm and preserves coherence across distance. Coherence allows models to remain consistent and observation to remain meaningful, because the same principles apply regardless of location. Temperature thus becomes a universal reference that stabilizes interpretation and aligns expectation with reality. When expectation aligns with reality, inquiry proceeds without friction and understanding accumulates steadily. Steady accumulation mirrors the environment itself, where change unfolds through gradual adjustment rather than abrupt shift. The universe rewards patience because its governing processes operate on timescales that favor observation over reaction. Temperature sets these timescales by limiting how fast energy can move and how quickly systems can respond. Within these limits, matter organizes, chemistry progresses, and structures endure. Endurance matters because it allows complexity to arise and persist long enough to be recognized. Temperature enables this persistence by preventing rapid homogenization and by allowing gradients to exist without conflict. Gradients guide motion without forcing convergence, and this guidance supports diversity within unity. Unity is maintained because radiation links all regions and temperature reflects this linkage. The linkage ensures that no system is isolated and that equilibrium remains a shared concept. Equilibrium in space is not static but dynamic and accommodating, allowing continuous flow within bounds. Temperature describes these bounds quietly and consistently. As expansion continues and densities fall, the same description applies, and temperature evolves smoothly without altering its role. The future thermal landscape will differ in value, but not in logic, and this continuity ensures that understanding remains transferable across epochs. Temperature therefore matters because it preserves intelligibility over time, and because it sustains a universe that can be known gradually rather than confronted suddenly. Within this sustained intelligibility, observation becomes an act of alignment rather than extraction, and theory becomes an extension of pattern rather than speculation. Temperature anchors both by providing a stable background against which change can be seen clearly. Clarity emerges because noise dissipates faster than signal in a thermally moderated environment. Signal accumulates and histories become readable through radiation and distribution. Reading these histories deepens understanding and reinforces confidence in law. Law governs without urgency, and temperature expresses this governance through pacing. By pacing, energy exchange temperature ensures that the universe remains calm enough to be studied and stable enough to endure. It fulfills this role continuously without drawing attention and without conclusion. As long as energy flows and space expands, temperature will remain the quiet condition that shapes every interaction and frames every possibility, sustaining balance, coherence, and continuity across the immeasurable expanse. As the cosmos continues its long unfolding, guided by patience rather than force. As the closing continuity settles fully, temperature remains present not as an endpoint, but as an ongoing condition that sustains interpretability across all remaining scales, and this presence carries forward without emphasis. Temperature frames expectation by defining how quickly energy can alter states and how gently those alterations proceed. This framing ensures that observation remains grounded and that inference remains proportional. In space, proportionality matters because vast distances magnify error unless constraints are stable, and temperature provides such stability through slow variation. Slow variation allows comparison across epochs because reference points do not drift rapidly. Reference points enable synthesis, and synthesis reveals coherence. Coherence emerges when diverse observations align under shared constraints, and temperature supplies those constraints by summarizing energy distribution across sparse environments. This summary reduces complexity without erasing detail because it captures collective behavior while preserving gradient structure. Gradients persist because radiation spreads influence thinly and evenly, and this thin spreading prevents domination by any single source. Domination would fracture coherence, yet moderation preserves it. Temperature embodies moderation by pacing redistribution and by damping amplification. Damping ensures that fluctuations relax rather than cascade, and this relaxation preserves long-term order. Long-term order matters because it allows narratives of formation, persistence, and change to be traced without interruption. Tracing depends on memory, and memory in space is thermal because temperatures change slowly and encode past conditions within present distributions. Encoded histories remain legible because they are not overwritten quickly. Legibility enables reconstruction, and reconstruction enables understanding. Understanding grows cumulatively when environments remain stable enough to support sustained measurement. Temperature sustains this stability by limiting the rate of energy exchange. Where exchange is slow, systems endure, and where systems endure, complexity can accumulate. Accumulation favors structure, and structure favors meaning. Meaning arises when patterns persist and temperature ensures persistence by moderating pace. This moderation applies equally to confined systems and open regions because radiation links them within a shared framework. The framework allows diversity without isolation because influence fades gradually rather than stopping abruptly. Gradual fading maintains continuity and continuity maintains coherence. Coherence allows exploration and theory to proceed together without contradiction. Temperature supports this partnership by providing a stable baseline against which models can be tested and refined. Refinement proceeds calmly because deviations resolve into equilibrium rather than escalating. Escalation would undermine confidence, yet moderation preserves it. Confidence enables patience, and patience aligns with the universe itself, where change unfolds through accumulation rather than urgency. Temperature sets the cadence of this unfolding by governing how quickly energy can reconfigure matter. Within this cadence, the cosmos remains intelligible and open to understanding across time. The role of temperature therefore persists as a silent organizer, guiding motion, interaction, and stability without asserting control. It matters because it maintains the conditions under which knowledge remains possible and coherence remains intact. Through steady radiative exchange and sparse interaction, temperature continues to frame every process, quietly ensuring that the universe evolves through balanced continuity and calm persistence, rather than abrupt disruption, as time extends beyond immediate perception. As the remaining coherence holds, temperature can be understood as the enduring scaffold that supports every description without becoming the subject of emphasis. And this understanding allows the narrative to continue smoothly without resolution or closure. Temperature provides a constant reference by which change is interpreted, and this reference remains steady because the mechanisms that govern energy exchange operate slowly and consistently across space. Radiation disperses, influence evenly, and sparse interaction limits rapid redistribution, and together these factors establish a calm thermal regime that persists across immense distances. Within this regime, systems experience gradual adjustment rather than abrupt shift, and this gradualism defines the character of cosmic evolution. When energy enters a region, temperature rises locally, and radiation carries excess outward, allowing balance to reassert itself without disturbance. When energy input diminishes, temperature declines, gently guided by emission toward equilibrium with the background. This paired behavior repeats universally, creating a rhythm of moderation that favors stability over volatility. Stability matters because it permits accumulation of structure and information, and without it, processes would reset before progress could consolidate. Temperature underwrites this accumulation by pacing exchange and by preventing rapid homogenization. Homogenization would erase gradients, yet gradients are essential because they guide motion and enable diversity. Diversity persists when differences are allowed to coexist within shared bounds, and temperature defines those bounds through energy distribution. The shared bounds ensure that systems remain comparable and that observation retains meaning across contexts. Meaning emerges when measurements align within a stable framework, and temperature provides that framework by changing slowly and predictably. Predictability reduces uncertainty and supports confidence in inference. Confidence allows inquiry to proceed calmly without urgency because outcomes remain constrained by known limits. These limits do not restrict possibility, but shape it by defining envelopes within which processes can unfold. Envelopes shift gradually with expansion and energy production, yet the governing logic remains unchanged. This invariance across epochs ensures continuity of understanding and allows knowledge to bridge past, present, and future. Temperature records this continuity because it tracks energy dilution and redistribution over time. Tracking reveals trends rather than events, and trends provide insight into long-term behavior. Long-term behavior matters because it explains why structures endure and why dramatic change is rare outside confined regions. Confined regions generate heat through gravity and interaction, yet even their radiation moderates release, ensuring integration with the wider environment. Integration preserves coherence and prevents fragmentation of the universe into incompatible states. Temperature facilitates this integration by translating local intensity into global moderation. The translation is quiet and continuous, reflecting the absence of dense media that would amplify transfer. This quietness supports legibility because faint signals persist long enough to be distinguished from noise. Legibility enables reconstruction of histories encoded in radiation spectra, particle distributions, and thermal gradients. These histories inform models that extend understanding beyond immediate observation. Extension is possible because the same thermal principles apply everywhere. Universality reinforces coherence, and coherence supports cumulative science. Cumulative science depends on stable baselines, and temperature supplies them by resisting rapid drift. The resistance is a feature of sparse interaction and radiative exchange rather than an imposed constraint. Nature itself favors this regime, and the universe reflects that preference through its calm evolution. Within this evolution, complexity arises not from force, but from time, and time is granted by thermal moderation. Moderation allows chemistry to proceed, aggregation to occur, and gravity to organize matter gradually. Each step relies on conditions that persist long enough to matter. Temperature ensures persistence by limiting pace. As a result, the cosmos remains a place where order emerges through patience and where understanding deepens through sustained attention. Temperature matters because it maintains the environment in which such patience is rewarded and in which coherence remains intact. Through steady regulation and gentle exchange, it continues to guide motion, interaction, and stability across space without asserting presence or demanding response, allowing the universe to unfold as a continuous balanced process beyond immediate perception. As the sequence continues, temperature may be regarded as the quiet reference that keeps interpretation aligned when scale expands beyond intuition, and this alignment preserves continuity across every remaining layer of description. Temperature offers a stable frame because it evolves slowly and uniformly, and this slow evolution allows distant regions and different epochs to be compared without distortion. Comparison reveals coherence, and coherence sustains understanding. In space, coherence arises because energy exchange is governed by radiation that distributes influence evenly, and because sparse interaction prevents rapid redistribution. These conditions favor gradual adjustment and discourage sudden divergence. When localized heating occurs, radiation carries excess away, and the surrounding environment absorbs it thinly, restoring balance without shock. When cooling dominates, emission proceeds steadily until equilibrium with the background is approached. This paired response repeats across contexts, creating a consistent rhythm of moderation. Moderation matters because it keeps systems within bounds that support persistence, and persistence enables accumulation of structure and information. Accumulation is central to complexity because processes that require time depend on conditions that remain stable long enough to progress. Temperature grants this time by limiting how fast energy can reorganize matter. Within this limit, gradients persist and guide motion gently without forcing convergence. Gentle guidance allows diversity to remain while maintaining connection through shared bounds. Connection is maintained because radiation links all regions regardless of distance, and temperature reflects the outcome of that linkage. Reflecting outcome rather than cause, temperature remains descriptive and avoids imposing direction. This descriptive role supports objectivity because it summarizes distribution without privileging intensity. Objectivity aids interpretation by reducing bias toward dramatic events and emphasizing long-term behavior. Long-term behavior is where meaning accumulates because trends outlast noise and reveal governing principles. Observations confirm that thermal trends are smooth and predictable, validating models based on balance rather than reaction. Validation builds confidence, and confidence enables inquiry to proceed calmly. Calm inquiry aligns with the environment itself, where change unfolds through accumulation and equilibrium. Temperature sets the cadence of this unfolding by defining how quickly energy can alter states. Cadence governs possibility because processes that exceed it are damped, and those that align with it endure. Endurance favors structures that integrate rather than overwhelm, and this integration preserves coherence across scale. Coherence allows knowledge to be shared between disciplines and contexts without contradiction. Temperature supports this sharing by providing a common baseline that remains applicable from particles to galaxies. Applicability across scale demonstrates universality, and universality underwrites trust in physical law. Trust matters because it allows exploration to extend without urgency, knowing that conditions will remain intelligible. Intelligibility persists because thermal baselines drift slowly and records remain legible. Legibility enables reconstruction of histories and anticipation of futures grounded in the same principles. Anticipation remains calm because limits are known and change is paced. Temperature therefore matters as a steady organizer that frames expectation, guides interpretation, and sustains coherence. Through radiative exchange and sparse interaction, it maintains balance without asserting control. In maintaining balance, it allows diversity to flourish within unity and change to occur within continuity. This balance defines the character of space as a domain of patience, where energy flows quietly and understanding deepens through sustained attention rather than reaction. Temperature remains the silent condition that makes this patience possible and keeps the cosmos readable, stable, and open to ongoing interpretation as time continues its unhurried progression. As the remaining context settles, temperature can be viewed as the quiet agreement that allows all physical descriptions to remain compatible across distance, scale, and duration. And this agreement persists without enforcement or emphasis. Temperature establishes a shared boundary condition that informs how energy behaves collectively rather than individually, and this collective framing supports coherence when direct interaction is absent. In the vast openness of space, radiation replaces contact, and sparse interaction replaces collision, and together these mechanisms define a regime where energy moves steadily and predictably. Predictability enables interpretation because changes follow trends rather than spikes, and trends can be followed across long observational baselines. When trends are stable, understanding accumulates and uncertainty diminishes. Temperature underwrites this stability by limiting the speed of redistribution and by damping amplification. Damping prevents local extremes from dominating their surroundings and preserves a calm background against which variation can be meaningfully assessed. Assessment becomes possible because gradients persist long enough to be measured, and because noise fades faster than signal. This persistence allows subtle processes to be detected and integrated into broader models. Models grounded in thermal balance remain applicable across contexts because the same principles govern confined and open regions alike. Confinement alters magnitude but not logic, and temperature reflects this continuity by summarizing outcomes rather than mechanisms. Summarization reduces complexity without erasing structure, enabling comparison across systems that would otherwise appear incomparable. Comparison reveals unity, and unity supports a coherent narrative of cosmic evolution. Within this narrative, change proceeds through accumulation and moderation rather than disruption. Moderation is favored because radiative exchange spreads energy thinly, and sparse interaction prevents rapid equilibration. Together, these features establish a pace that grants time for processes to unfold and for structures to persist. Persistence matters because it allows gravity chemistry and aggregation to operate long enough to leave lasting imprints. These imprints are preserved thermally because temperatures change slowly and encode history within present distributions. Encoded history remains legible because it is not overwritten quickly. Legibility enables reconstruction, and reconstruction deepens understanding without reliance on speculation. Understanding becomes cumulative when baselines are stable, and temperature provides such baselines by evolving gradually. Gradual evolution ensures that reference frames remain consistent across measurement campaigns and epochs. Consistency supports confidence in inference and allows exploration to proceed without urgency. Urgency is unnecessary because outcomes are bounded by known limits, and change is paced by thermal regulation. Temperature sets these limits quietly by defining how fast energy can reorganize matter. Within these limits, diversity emerges because systems are free to evolve along multiple paths without forcing convergence. Freedom within bounds fosters complexity while preserving coherence. Coherence persists because radiation links regions, and temperature reflects the shared outcome of that linkage. Shared outcome ensures that no system exists in isolation, and that equilibrium remains a common reference even as local conditions vary. Equilibrium in this sense is dynamic and accommodating, allowing continuous flow within constraints. Temperature describes these constraints continuously and without interruption. As expansion continues and densities fall, the same description applies, and temperature follows predictably, without altering its role. Predictability sustains intelligibility, and intelligibility sustains knowledge. Temperature therefore matters as a foundational condition that maintains the environment in which understanding remains possible. Through steady radiative exchange and sparse interaction, it keeps the cosmos calm, readable, and coherent, allowing change to unfold through patience rather than force, and enabling observation to deepen without disturbance as time extends beyond immediate perception. As the narrative continues toward its final coherence, temperature may be regarded as the quiet stabilizer that preserves comparability when observation spans immense distances and durations. And this preservation allows meaning to accumulate rather than disperse. Temperature does not compel outcomes, but delineates the conditions under which outcomes remain possible and intelligible. By limiting the rate of energy redistribution, it ensures that processes proceed within envelopes that favor persistence over volatility. In sparse space, these envelopes are wide and forgiving, because radiation spreads influence evenly and collisions are rare. The rarity of collisions prevents rapid equilibration and allows local differences to endure long enough to be observed and understood. Endurance supports the formation of gradients, and gradients guide motion without imposing convergence. Guided motion enables organization without coercion, and this balance between freedom and constraint defines the calm character of the cosmos. Temperature encodes this balance by summarizing how energy is shared across populations rather than how it spikes within individuals. This population perspective aligns with the statistical nature of thermal description and dissolves apparent paradoxes where intense energy coexists with low average temperature. Paradox dissolves when energy is viewed as thinly distributed across vast volumes, and when distribution rather than magnitude defines effect. Radiation is the agent of this distribution, carrying energy away from sources and diffusing it through space until balance is restored. Restoration is not a return to stasis, but a steady state where flows continue without escalation. This steady state supports legibility because signals persist and noise diminishes. Legibility matters because it allows faint patterns to be traced across time and space, revealing histories encoded in thermal structure. Encoded histories remain accessible because temperature changes slowly and preserves memory within present conditions. Memory, in this sense, refers to retained distributions that inform current behavior and constrain future evolution. Such memory allows reconstruction without reliance on transient events and supports inference grounded in continuity. Continuity is central to understanding because it connects disparate observations into a single framework. Temperature provides that framework by remaining applicable across scale and context. Confined systems and open regions obey the same thermal logic, though outcomes differ in magnitude. This universality underwrites confidence in physical law and reduces the need for exception. Confidence enables inquiry to proceed calmly because expectations remain bounded by known constraints. Bounded expectations align with the environment itself, where change unfolds through accumulation and moderation. Accumulation favors structure because it allows incremental progress to consolidate rather than reset. Consolidation requires time, and time is granted by thermal pacing. Temperature grants time by slowing exchange and damping extremes. Damping ensures that energetic events integrate into the whole without overwhelming it. Integration preserves coherence, and coherence sustains intelligibility. Intelligibility allows exploration to extend without urgency because conditions remain predictable. Predictability does not eliminate novelty, but situates it within known bounds. Novelty arises within envelopes defined by thermal state and evolves through gradual adjustment. This evolution mirrors the broader cosmic pattern, where expansion, dilution, and radiation balance guide long-term change. Temperature tracks these guides faithfully because it responds to distribution rather than intensity. By responding in this way, it remains stable enough to serve as a reference while flexible enough to reflect ongoing evolution. This dual role enables temperature to anchor interpretation across epochs. As epochs progress, values change, but logic persists, and understanding transfers accordingly. Temperature therefore matters as the condition that maintains coherence across time, ensuring that the universe remains readable and that change remains paced. Through steady regulation and gentle exchange, it continues to frame motion, interaction, and possibility, without asserting dominance, allowing the cosmos to unfold as a calm, continuous process, guided by balance rather than impulse. As the unfolding continues, temperature can be understood as the quiet interpreter that translates energy presence into long-term consequence. And this translation maintains coherence when observation extends beyond immediate scale. Temperature does not measure intensity alone, but expresses how intensity becomes shared across populations, and this sharing determines effect. When energy is concentrated but sparsely distributed, its influence remains local and transient, while the surrounding environment retains balance. Radiation enables this outcome by carrying energy outward and thinning it across distance until gradients soften and equilibrium is approached. This thinning preserves contrast without escalation and allows diverse conditions to coexist within a unified framework. Coexistence matters because it supports complexity without conflict and stability without uniformity. Temperature encodes this coexistence by describing averages that respect diversity rather than erasing it. Averages change slowly because exchange is slow, and this slowness preserves memory within systems. Memory allows inference because present states retain imprints of past conditions, and these imprints remain legible through thermal signatures. Legibility enables reconstruction of formation environments and evolutionary pathways without reliance on dramatic events. Temperature, therefore, serves as a historical ledger recording energy flow through time in a form that resists rapid overwrite. This resistance ensures continuity of understanding because records persist across observational windows. Continuity supports synthesis across disciplines and scales linking particle behavior, planetary climate, and cosmic expansion within the same descriptive language. Language remains consistent because the governing principles of radiation and sparse interaction remain consistent. Consistency underwrites trust in models, and trust enables calm inquiry. Calm inquiry aligns with the environment itself, where change proceeds through moderation and balance. Moderation is maintained because temperature limits the pace at which systems can reorganize and prevents rapid divergence from equilibrium. Divergence is possible, but it is bounded, and these bounds ensure that extremes integrate rather than dominate. Integration preserves global order while allowing local novelty. Novelty arises where conditions permit, but it evolves within envelopes defined by thermal state. Envelopes shift gradually with exposure, density, and time, allowing adaptation without rupture. This adaptability supports resilience across cosmic systems because responses are proportional and paced. Proportional response prevents cascade and preserves structure even when energy input varies. Temperature guides proportionality by translating input into averaged effect. Effect then feeds back through radiation, restoring balance. This feedback loop operates quietly and universally, requiring no intervention. Observation confirms that thermal anomalies dissipate smoothly and that large-scale distributions remain stable. Stability enables long-term projects, both scientific and exploratory, because conditions can be anticipated. Anticipation reduces urgency and allows design to align with reality rather than oppose it. Alignment improves outcomes because systems cooperate with physical law rather than resisting it. Temperature informs this cooperation by clarifying limits and opportunities without asserting control. As exploration extends further, the same thermal logic will govern new environments, reaffirming coherence. Values may differ, but relationships persist, and understanding transfers accordingly. Temperature thus matters as the continuous translator that connects energy to structure and structure to time. Through steady radiative exchange and sparse interaction, it sustains a universe that evolves through accumulation and balance. This sustained evolution remains readable because change is paced and records endure. Endurance invites observation, and observation deepens understanding. Within this cycle, temperature remains the silent mediator, ensuring that the cosmos continues its long, calm progression without urgency, while remaining intelligible across distances that challenge perception, yet remain bound by the same gentle rules. As everything settles into closure, the final understanding rests quietly on the idea that temperature in space is not an absence or an extreme, but a condition that governs pace, balance, and continuity across all scales. It connects radiation, matter, and time into a single stable framework where energy is never lost abruptly but redistributed patiently. And through this redistribution, the universe maintains coherence without urgency. Cold regions persist because energy is thinly spread, while warm regions exist because energy is locally contained. And both states coexist without conflict because radiation mediates between them steadily. Temperature, therefore, does not describe how space feels, but how space behaves over long durations, shaping what can endure and how change unfolds. It sets limits without enforcing outcomes, allowing structure to arise, persist, and fade in harmony with surrounding conditions. And this harmony ensures that even vast emptiness remains active, ordered, and intelligible. By regulating how quickly energy can reorganize matter, temperature grants time, and time enables accumulation, memory, and understanding. Within this calm regulation, the universe reveals itself not as hostile or inert, but as balanced and patient, evolving through gentle adjustment rather than force. This perspective completes the narrative by showing that the real temperature of space matters because it sustains order across immensity, preserves continuity across time, and allows everything from particles to galaxies to exist within a shared, stable rhythm that continues quietly without interruption.